In this film, we'll find out more about what happens in modern power stations, and we'll look at a quite different way of providing the energy needed for the generation of electricity. Many power stations depend upon burning fossil fuels, coal or oil, to raise steam to drive the turbo generators. Here at Wylfa, on the Anglesey coast, there's one of Britain's nuclear power stations, which depends upon a very different process. This is the roof of the huge building which contains 2 nuclear reactors. Inside, there's a vast open space with the tops of the reactors visible at each end. Here's one of them. In the control room, engineers keep strict control of the processes going on in the reactor, so that it provides just the right amount of heat to raise the steam needed for the generators in another building. Each end of the control room looks after one of the 2 reactors. Inside the reactor, gas is being heated up to nearly 350 degrees C by the nuclear reactions taking place there. Screens display the temperatures in different parts of the reactor. This is a sort of plan view, showing what's happening deep down inside the reactor. What does the fuel look like? There are nearly 100,000 of these fuel elements in the 2 reactors. They contain uranium and only heat up when they're all placed in exactly the right pattern inside the reactor. These fins are there to hold them in place. Gas circulates around the elements, taking the heat away as it passes along these grooves on the surface of the casing. Here's a simplified diagram of the boiler arrangement. There are boiler tubes through which water passes, separated by a shield from the reactor. The reactor produces heat and gas circulates around the fuel elements, carrying the heat to the tubes, so that steam's produced and passes out to drive the turbines. The gas used to transfer heat from the reactor to the boiler tubes is carbon dioxide, CO2. It arrives at the power station in big tankers carrying the liquefied gas, and it's stored in tanks until it's needed. The reactors are each enclosed in thick concrete shells inside the reactor building. There's no noise coming from it, but it's generating heat by nuclear reactions going on in the fuel elements and producing steam like the coal-fired boilers we looked at in another film. This steam passes through pipes to the generator building. In the control room again, we can see the temperature of the steam coming from the boilers. It's about 320 degrees C. There are no chimneys because a nuclear reactor produces no smoke, so there's no need for the big electrostatic precipitators we saw at the coal-fired station. But in fact, a lot of small precipitators are used in a nuclear power plant. Here are some of them at Wylfa. They're to test the carbon dioxide which is circulating around the fuel elements in the reactors. If an element should develop a fault and particles of radioactive solid got into the carbon dioxide, a precipitator would collect these solid particles just as if they were ash particles in smoke, and their radioactivity would be detected. This would show that something was wrong in the reactor, and the right steps could be taken to prevent any damage. Instruments in the control room show if the precipitators are picking up any radioactivity. This is just one of the precautions taken in nuclear power plants to make them safe as well as efficient. But many of the instruments in the control room are like those in, say, a coal-burning plant, because it's only the way in which the steam's produced that makes nuclear power stations different. The steam's used to drive turbines which drive generators, just as in all power stations. Here's a gauge showing us the turbine speed, around 3,000 revolutions per minute. And here we are in the generator hall, where the electricity is being produced. This is a smaller station than the coal-fired one, but it still produces 1,000 million watts of electricity. Let's look at the generating equipment. Here's the inside of one of the turbines, removed for servicing. You can see that there are many sets of blades. These are turned by the hot steam expanding through the turbine housing. The same kinds of turbine are used however the steam's been generated, in a coal-fired boiler, say, or in a reactor, as here at Wylfa. There's a turbine like the one we've just seen inside this casing, driven by high-pressure steam straight from the boiler over in the reactor building. The steam emerging from that first turbine then passes to low-pressure turbines, all helping turn the same shaft. The big pipes above carry this low-pressure steam to these turbines. The turbines do the same job as the crank in that laboratory demonstration in the last film. They drive this AC generator, which consists of a big electromagnet rotating inside an arrangement of coils. The electromagnet rotates, not the coil as in the lab model, but the effect is the same. The model used a permanent magnet. The big generator uses an electromagnet. So there has to be a sort of mini generator, called the exciter, to power this electromagnet. Here it is at the end of the shaft. All modern power stations have sets of turbines driving generators. We've seen the same kind of equipment in use in a big coal-fired station in the earlier film. Our lab demonstration model produced only a very small current, led by quite thin wires to the galvanometer or oscillograph we used to detect it. Power station generators produce vastly more electrical current. Here at Wylfa, you can see the casing round some of the cables, taking the current out from the generator hall. After raising its voltage, we'll be coming to that in a few minutes, the current is led to the pylons which carry it across the country in the national grid system. At Wylfa, there are some noticeable differences from coal-fired power stations. For one thing, no railway tracks. 1,000-ton coal trains aren't needed every hour, as they are at Fiddler's Ferry. Quite apart from the trains and the great coal stocks, there are these giant cooling towers at our other power station. What are they for? Do you remember that when the steam's passed through the turbines, it's cooled in a condenser to turn it back into water to be returned to the boilers? The condenser circulating water coming out at the top has to be cooled so that it can be used again. It's this condenser circulating water, not water coming from the boilers and the turbines, which is cooled in the cooling towers. These are great hollow concrete chimneys of a special design, as we'll see. A lot of water gets lost as water vapor from the tops of the towers, so there's got to be a constant topping up with water from, say, a nearby river. Inside the towers, the condenser circulating water falls like rain, and it's cooled by a current of cold air passing up the tower. The water came out from the condenser at about 30 degrees C, and this cools it to about 20 degrees C, ready to go back again. The water is sprinkled down from about a third of the way up the tower. Above this, there's just a great hollow space. The sides are curved inwards near the top, and it's this particular shape which produces a constant flow of air drawn in at the bottom and out at the top. Cooling towers are a prominent feature of many inland power stations. However, because Wylfa is by the sea, there are no cooling towers, and seawater is used to condense the steam coming out of the turbines. It's returned to the sea when it has passed through the condensers. This does no harm to marine life. The condensers are underneath the turbines. Now all this means that a lot of heat's wasted in a power station. That's one reason why you only get about 25% of the heat energy produced in the Wylfa reactor turned into electrical energy, while a coal-fired station can turn about 35% of the energy of the coal into electricity. This loss of heat can't be avoided. It's a basic law of physics. Think of all the heat wasted from the top of the cooling towers, for example. There's another kind of waste from a coal-fired station. Thousands of tons of ash are produced every day. This is removed from the precipitators, mixed with water, and pumped along pipes into huge lagoons lined with concrete. As the solid matter settles out, the water can be pumped off and used again. Eventually, the lagoons filled up with ash and all the water's taken away. Huge deposits of waste are left. One of the big problems about burning coal is not only the cost of the stuff, but what to do with the thousands of tons of waste ash that's left. Some of it can be sold, for road making, for example. Here's work on a new motorway interchange, and they're using many lorry loads of power station ash, but there's not nearly enough road making to use up all the ash that's produced. Making electricity means using up other fuels. The power goes out across the pylons, and each one of these empty wagons means that 30 tons of coal have been used up. The scene at a nuclear power station is very different. Each fuel element lasts up to 2 years and can then be reprocessed to provide more material for the nuclear industry. A road is all that's needed to bring in fresh fuel occasionally and remove waste. But the waste is radioactive, and great care must be taken with it. This model demonstrates an important feature of electricity transmission, sending it out to where it's needed. Look at these two lamps, one shining much more brightly than the other. Let's look at the power station end. The same current's fed to two lamps which shine equally brightly. It's also fed at a voltage of 6.5 volts along one of two transmission lines. Now, when electricity passes along a conductor, some power gets wasted in heating the wire. And the longer the conducting line and the higher the current, the greater the loss. So see what happens at the end of our line. The bulb glimmers only feebly. A second line is fed through a transformer which raises the voltage to about 83 volts, much higher than before. The line's the same length as the first one, but there's less power loss at a higher voltage because the current is smaller. It's transformed down again to 6.5 volts, and because there's been a smaller loss, the lamp shines much more brightly than the first one. Compare the two. The lamp fed along the high voltage, and therefore low current line, is much brighter. Here's a demonstration transformer. It has a soft metal core, and we'll surround one side with a primary coil of 1,200 turns of wire connected to the 240-volt alternating current mains. Then first, we'll put a 5-turn secondary coil on the other side. We complete the iron loop so that it's continuous and connect the secondary coil to a voltmeter. Read the top scale. We get a voltage of just less than 1 volt from the secondary coil. Now we put on a secondary coil with 10 turns. We get a voltage of nearly 2 volts from this secondary coil. Finally, a secondary coil with 15 turns. This gives us a secondary coil output of nearly 3 volts. You can work out the connection between the primary coil voltage, the number of turns in the 2 coils, and the output from the secondary coil. This was a step-down transformer, reducing the voltage. Transformers at power stations are very much bigger. They're used to step up the voltage from the generators to a much higher value to reduce power loss in the long transmission lines of the grid system. Here, it's been stepped up to 275,000 volts. It's sometimes transmitted at 400,000 volts over the supergrid network. The voltage can be stepped down by other transformers at substations along the line, and then distributed to the houses and factories and so on, where it's used. In Britain, the railways use enormous quantities of electrical power. The overhead electrification system carries electricity at 25,000 volts. Inside the locomotives and other traction units, this has to be transformed down before it's supplied to the driving motors. So, transformers have to be fitted. At British Rail Engineering Limited, Crew Works, a big transformer's being fitted to a locomotive.
Ready?
It's a very heavy piece of equipment and takes up a lot of space inside the locomotive.
Whoa.
But it's worth doing things this way because the disadvantage of the extra weight to be carried is more than made up for by the greater efficiency of electric power distribution at a high voltage. If the system were supplied at a low voltage, the transformers wouldn't be needed, but then there'd be a great waste of power in the long overhead wires. Another good example of physics in action. Modern industrial nations must have electrical power for transport, lighting, running machinery, and many other purposes. To produce that power, other kinds of energy must be used up. You can't get anything for nothing. Coal burning is expensive, produces a lot of waste, and coal won't last for very much longer. Oil and gas will last for a much shorter time. Nuclear power may be very important in the future. Many people are afraid of it. Try to understand it, the advantages and disadvantages, before you make up your mind.